extra excited today because I have met Dr. Aakash Agarwal at some summary schools and have seen his talk, and he is a great mentor as well. So before proceeding ahead, I would like to mention a few general instructions for our audience. So kindly keep your mic off to avoid any disturbance while the talk. And you can all drop your doubt and queries in the chat box if you are joining from other social media platforms. If you are joining from Google Meet, then you can just raise your hand and then turn on your mic uh, for asking any question. And at the end of the talk, we'll float a link to fill your attendance. So make sure to fill your attendance at the end of the talk. So with this, I'll now hand over uh, to Dr. Agarwal. Welcome, Dr. Agarwal.
Yeah, thank you for having me here, and thank you all for attending. So let me start by sharing my screen, and I hope my voice is clear. Also, I believe that this topic may be new to many of you, so please don't hesitate if you want to if you have any questions, please feel free to raise them in between. And yeah, even if it's a silly question, because because it's a neuroscience may be a new topic for you, and I would like you to enjoy this talk. Okay. So the topic that I'm working on is to understand how do we recognize words or printed text on a screen or or a paper as well. So, reading may seem trivial to us, but it's not an easy task. And this cartoon would illustrate the challenges a computer has to face when it's recognizing a text. So although we have no issue in recognizing these letters, although they're distorted, computers fail at this miserably, and that's why the captchas are present. So when you look at the brain, when human brains look at a captcha, so the information from the eyes reaches a part of the brain in the back of the head known as visual cortex. And a lot of research have shown that there are multiple stages of processing in the visual cortex, starting with the processing of oriented lines, Gabor feature banks, to simple shapes like square circles, color feature processing, and the whole object processing. And this is present in all the humans, both literates and illiterates. But when you learn to read, a part of this visual cortex is reprocessed to process words, and it is known as visual word form area. And this region is present only in literates and not illiterates. And then you have other regions like language comprehension and speech areas, and there are a lot of other brain regions which are involved in word processing. But recognizing words is not only to recognizing distorted characters. You can read even if you replace letters with numbers, like in this example. I'm sure many of you would have seen this in social media. And this is another example where they say if you as long as the first and the last letters are same, and if you jumble the middle letters, you don't have any difficulty in reading. And this kind of illustrations kind of indicate that okay, human mind doesn't read every word by itself, but word as a whole. I think the results that I would show would try to disprove this hypothesis and show that we process every letter and process them in parallel, and that's why you get the perception of reading the word as a whole. So let's assume if this was true, the one on the right side, then if we try to build a process of how the word recognition models would take place, we'll have lines or simple features combining to form letters, then letters combining to form two letters, two-letter detectors, and then further combine to form whole words. But alternatively, if we are processing only letters and there's no intermediate step of letter combination detectors, then we would have one on the right, where letter parallelly processed parallelly to recognize words. So the question is how do we recognize the representations in the brain to understand to differentiate between these two hypotheses? If you're doing a brain imaging experiment, what you do is you show an image to a person and then record a brain activity. And let's say if each box over here could be thought of as a single neuron or voxel or whatever response unit, then let's say for image 1, we get a certain response activity pattern. Now we show the second image and we get another activity pattern. Now, if these two images are perceived to be similar, then the activity patterns would be similar. But if they're different, then you would see like totally different activity patterns in this image compared to this image. And just by comparing the dissimilarity between the activity patterns, we could say, okay, whether the images shown to the person is perceived to be similar or not. But again, like neuroimaging experiments are expensive, and like uh, you don't. Doesn't always give the insight that we want to do. So we could arrive at similar conclusions using behavior experiments. And what we do is visual search. So in this search array, there are two oddball targets, and I guess you'd have noticed that finding W is quite easier compared to finding T. And so usually when people come to lab, we like ask them to do this task, and what we record is the response time. And so the dissimilarity is the inverse of response time. If the two shapes are very similar to each other, then you'll take longer to respond, which means that 1 over response time is small. So the dissimilarity values is small, which means they're very similar. And if the response time is less, then they're more dissimilar. I hope this part is clear. And so now what? So if we so so now we wanted to understand the dissimilarity space of letters. And so coming back to the question of why are we able to read jumbled words? So I think it may not have to do anything with the language processing, but with the help, it's mainly because of the visual similarity, and this kind of illustrates that. So in this example search array, if I just don't ask you to find an odd or not and not focus on reading, you would notice that finding OFRGET is easier to detect than FOGRET. And if you again try to visualize this data in the reaction time that you was in which perceptual space, you would see that forget and forget are visually similar compared to forget and OFRGET based on just purely reaction time, which kind of indicates that the visual similarity of the word with the middle jumbled word is more similar compared to the edge jumbled word. And even if you ignore whether you know the word or not. But this is one example. This is only an illustration, and we wanted to understand okay, does this generalize for any letter combinations, or can we build a model of it? And to do that, we want first to understand the letter representations in the brain. And so to do that, we again do a visual search task, and this is what a person sees on a screen. This all is one oddball, and which are surrounded by distractors. And the task is to find an odd or not. And we did all possible search combinations, and we created this visual search space for letters. And you could notice you could see the letters which are close by are perceived to be similar, and letters which are far apart are very dissimilar in perception. And also you notice some interesting patterns. As you move along the x-axis, the letters become more curved. So the curvature increases along the x-axis. And as you move along the y-axis, then the number of edges decreases. There are more edges in this case, junction, and there are one edge on the top. And so, any questions here? No, okay. So now we wanted to we assume that so let's assume that the dimensions that we have here are the responses of neurons. So let's say if we have neuron 1, then the activity along this axis would be the responses to artificial neurons. So these are not real neurons. We assume that the axis along the multidimensional scaling is the responses to individual neurons. So now with this response, we wanted to understand can the activity of single units combine to predict the activity of bigrams and so on. So the hypothesis is so this is the schematic of the model. Let's say we have 3 letters, and we do the responses of those 3 letters based on our previous experiment. And now we wanted to predict the response of 80. Then what we would predict is that the response of 80 is a linear combination of weighted sum of response of letter A plus response of letter T for the first unit neuron, and similarly for the second neuron, we have the response of A plus response of T. And we could do that for any other letter combinations as well. And the dissimilarity between any 2 bigrams, in this case AB and CD, would be just the absolute difference between the responses that are predicted here. So you have weighted sum of response of A plus B minus weighted sum of response of C and D. So in this experiment, we like chose 49 bigrams and we collected like 1176 searches. And this 49 bigrams were chosen that such that there were some of them were real words and some of them were just letter combinations. And what we saw that like with this model, it could predict the data quite well. So on the y-axis, we have the observed dissimilarity, which is we got from the experimental data. And on the x-axis is the model predictions. And I have highlighted some of the words which are used in the bigrams. And so if you notice that this model doesn't have any assumption about the letter combination, it only says that the response of bigram is a linear combination of individual letter responses. And uh, if words or bigrams were special, then we should have seen a deviation from the model fits, but we don't see that, which kind of indicates that bigram dissimilarities can be predicted using single letters. Okay, so next we wanted to like further prove our hypothesis. So we created words by combining three letter words. So you could see like so along the diagonal are the 6-letter words, and which are made up of like individual 3-letter words. And again, the question was like, and which model predicts this data well? Like, is it the letter model or the trigram model where we explicitly like predict the responses of the 6-letter strings using the 3-letter words? And over there as well, we didn't see any specific deviations between the model predictions of the using the letter model. And in fact, the model predictions way better than the diagram-based model. Moreover, there's a popular distance metric in computer science known as Levenshtein distance. So OLD stands for orthographic Levenshtein distance, which kind of tries to measure the minimum edits required to move from one string to the other string. And it doesn't, since it doesn't have any account of the letter position or the shape of the letter, it performs poorly compared to other two models. So we could kind of like, I mean, so this kind of explains like, okay, words could be predicted using letters, and there's no intermediate step of n-grams. But at this stage, you may ask, okay, the task that we're doing is a visual search task, and we're not doing explicit reading task. So maybe when you're doing any language task, we may need to have this n-grams or letter combinations. So next we wanted to like, we did two like tasks which are involved in reading. One is like unjumbling the word, and others a lexical decision task. So in this unjumbling task, what we do is like we show a string on the screen, and we show it for 7 seconds or until they press a key. And the task the subject has to do is like they have to unjumble it mentally, and if they know the correct word, they press a key, and then they type out the response. And this way, we collected like the response time to unscrambling for a lot of different non-words. And you could see a nice pattern over here. Like some non-words are easy to unscramble compared to some others. And again, like, I mean, if all of this is arising because of the visual similarity, then we would predict that if the dissimilarity between the scrambled word and the real word is smaller, then you'll take it like it will take less time for you to unjumble this word compared to one which is very different. So that the response time that you get should be directly proportional to dissimilarity. More the dissimilarity, the higher the response time. And this indeed holds true. And if we also try to include some of the other lexical parameters like letter frequency or like bigram frequency, trigram frequencies, then it slightly improve the model predictions. But overall, the letter model itself can predict a lot of variability in the data. Okay. And so we see kind of like visual similarity is predictor of unscrambling time. And so now, similarly in the lexical decision task, it's a more like rapid task where when they see a string, they have to respond whether if it's a word or not a word. And over there as well, we see like certain patterns where like some words are easier to categorize as words compared to other, and similarly for the non-words. And if we try to model the word response time, we see that word frequency is the main predictor of the to predict the word response time, which indicates like which is kind of makes sense, because if you encounter the words more frequently, then it'll be easier for you to recognize those words. And that's how the advertisement also plays roles in our life. And then there are other factors which we try to model, and they don't predict as well as the word frequency. And now coming back to the modeling the non-word response times, what we see is that the non-words, if we try to predict them, so if they're very similar to the word, then you'll take longer to unjump to say that it's not a word. And so in this case, the response time would be inversely proportional to the dissimilarity. And and this indeed was the case, and we could use this to predict the non-word response time to compare, and the model fits were better than other models that we tested out. Um, so in general, what I've shown here is that, I mean, we see that to predict the response of words or non-words, we could use this letter model where we predict the response of word as a linear combination of individual letter responses, and that could be used to create a representation space which could predict like our reading speed when we like jumble the words, or if you replace like letters with numbers, or you could like even like play around with based on the how dissimilar the non-word is with the real word, and based on that you could predict like how slow a person would be in terms of reading or difficulty. Yeah. So any questions so far?
Yeah, there is a question in the chat box.
Yes.
Okay. Sridhar Pro, you can unmute yourself. Other participant also, you can ask your question.
Yes, am I audible?
Yeah.
Yes.
So I just want to ask one question, like, can we use the amplitude of any like ERP signals, like maybe in 400 coming from the brain, like to find
Mhm.
out the similarities and dissimilarities between two words or maybe two combinations or something?
Yes, I mean you could, but you need to know the population level analysis, because what you get from the N400 would be just a peak,
Hmm.
and that may not be very informative, because the peak could change because of the attentional effects as well. Like some words may evoke more attention than the others.
Hmm.
So in this case, it gets difficult.
Okay.
So in general, like if you do, um, like that's why EEG is not usually preferred. Like you do fMRI experiments, and I would show some of the fMRI results later.
Hmm.
But if you could somehow get like high density EEG signals, or like if you could do some like population analysis,
Hmm.
then maybe you could answer such questions. Yes.
Okay, sir. Thank you. So another question is like I was just thinking like instead of using visual representation of word, if we can
Mhm.
use like auditory response of the subject and apply the same model. In this case, maybe the similarities or dissimilarities occur due to the asset. Will the model works in same way?
We would think yes. I mean, I could give both yes and no answers.
Mm-hmm.
Currently my advisor Esperon is working on this to
Okay.
confirm it. But I mean, the reason, ideally, I would expect that the same thing would hold there as well. But one main difference between audio and vision is that, like, visually we could process things in parallel, but audio processing happens a bit more serially.
Mm-hmm.
So the models that I'm showing here could directly be applied to model the audio dissimilarities. But the patterns that we would get may differ from what you get for the vision.
Okay. So like in that case, we need more advanced model or something so that we can reduce the time.
Time as in,
Like
sorry, I didn't get.
the for the results, I think like if we want to measure the similarities or dissimilarities in case of auditory response, I was
Mhm.
thinking that we need some model which can reduce the computational time.
Right. Um,
Mm-hmm.
but these models are kind of simple because you're trying to predict the response, whatever of auditory word or visual word, using the letter combinations. And so it's relatively, it doesn't take a lot of time to fit these models.
Mm-hmm.
So it's about building the correct, um, the regression matrix, and then trying to predict that.
Okay, thank you,
Yeah.
sir, thank you so much.
Thank you. Yeah. Any other questions?
Hello.
Yes.
I'm sorry, I joined a bit later, and like I don't know what technique was used to get this data?
Sorry, what is?
I don't know what technique was used to receive this data from the brain.
So this is so far I have shown you some behavior evidence, like we did visual search experiments and lexical decision task or unscrambling task. So what I've shown currently is the behavior evidence. Next, I would show some fMRI data and also like how we model the neural networks which are trained to recognize words. Yeah. So if there are any questions specific to like this part, I can take now. Others, we could take more questions at the end. And please let me know if I'm going too fast or I need to slow down as well. Like, yeah. Okay. Yeah. Thanks. So next we wanted to understand like where is all this processing happening in the brain. So I have talked about in the beginning like these are the different visual and language areas, and we wanted to like understand like where each of this processing is happening. Like, is it happening in the word form area or is it in the visual cortex or where? And so these are some of the regions of interest. And what we do is like in the MRI scanner, we ask the person to lie inside the scanner, and using the projector, we show images on the screen. And we show like stimulus like letters and words, like what we see here. And because fMRI is it measures the blood flow, it's a bit slow response, and so you can't show images very rapidly. So you show it like once every 4 or 8 seconds. And once you so you record the brain slice by slice, and then each slice is made up of like 3D elements like voxels, which is like pixel is a 2D element, so voxel is a volume 3D element. And then like this is how a typical response profile would look like if you show a stimulus and wait for long term. So this is the hemodynamic bold response signal. And what we are interested is in just the peak response. Like, so if I show an image, what's the peak response that I get? And that is kind of an equivalent of the neural response. The idea is that whenever the neuron fires, it consumes oxygen, and to compensate for the loss of oxygen, there will be an increase in blood flow. And the amount of blood flow kind of it's an indirect evidence for the amount of neural activity in that region. So, this is how a typical signal looks like after a lot of pre-processing steps that we do. And we like tried, and then we estimate the peak responses and analyze that. So the first thing, so in the stimulus, so again, we were interested to understand like why are edge letters special, or like, so we identified some words which vary in different frequencies, and we created non-words by either substituting or transposing the middle letters, like jumbling them, or the edge letters. And as a control, we also do like a substitution where like we substitute the middle letters or we substitute the edge letters. And so we had like 74 such stimuli. Like we had 10 single letters from which these 64 words and 52 5-letter words and non-words were made. And like some of like we had 8 repetitions because the fMRI signal is very noisy. So first we wanted to look at the mean response for different categories. So we have regions, early visual areas, V1 to V3, and then a bit higher middle visual area, V4, the object processing areas, lateral occipital cortex, the word form area, and the language region temporal gyri. So as you'd expect in early visual area, the responses mainly depend on the size of the word. So that doesn't differentiate between words and non-words, but it responds more compared to the letters. And the same, so then we have a bit more selectivity for V4, but in lateral occipital areas, it doesn't differentiate between any of the word categories. So it's a bit more invariant response to the size. And in word form area, initially when we saw because you can say, okay, it's a word selective region, but it's responding higher to non-words. And why is it the case? And it was kind of a bit puzzling, but in literature, it's still not, although they say it's a word selective area, but it does respond to other object categories, although it responds higher to words. But also it depends, its activity is modulated by a lot of other factors. And I won't be discussing about that now. But now we wanted to understand which region gives rise to the response time. And we found that the mean word form area activity was one which highly correlated with the mean response time. And you could see for both words and non-words, the mean level of word formation activity could be correlated with the response time. And so we found that mean what VWF attack is a predictor of lexical decision time. Next, we wanted to understand the representation space. And now from the stimulus that we have, we could have different two possible representation space. One is like a visual representation space where you would where the trail and trial are visually similar compared to path. But if you look at the semantic space, the trail and path should be closer to each other compared to trial. And so we wanted to understand so we could create this visual space from the behavior experiments and the semantic space using language models like word-to-vec or globe feature vectors. And we wanted to understand which representation space of which area better matches the visual areas and the semantic space. And so we computed the perceptual dissimilarity from different areas and correlated that with the visual space. And we found that the higher visual areas, the lateral occipital areas, are the ones which better match the perceptual space. And if you look at the match to semantic space, then we see the correlation to be high in both language areas, but also in the lateral occipital areas. So to conclude, what we see here is that, the higher visual areas encode perceptual space for strings, and the temporal regions encode semantic space. And possibly we don't, from the fMRI, it's difficult to say, but we speculate that there may be some interactions between these two regions. And that could be the reason why we see some evidence of semantic space in the lateral occipital areas as well. And the lexical decision time is taking place in the words. And if you remember, the lexical decision time for non-words was it depends on the similarity to the words. If they're very similar to words, then it will take longer to say it's not a word. And so maybe there's some stored template, which I speculate may be coming from the language areas, and the incoming string so you have some template of a word, and the incoming string is being matched to the stored template, and the difference between the activities kind of indicates the VWFA response. And so this is a hypothesis that needs to be tested. But from fMRI, we got some evidence of which regions are involved in this lexical decision task and perception of word space. Any questions in the fMRI part? I hope it was clear. Okay, if there are no questions, then let's go to the third part where, we wanted to understand what happens in the neural networks. So in both the methods that I showed, in behavior and word fMRI, we can't look at the activity for individual neurons. In word behavior, what we get is the output of what happens across multiple brain regions. In fMRI, we could look at some of the brain regions, but at higher resolution, a bit higher resolution, because each voxel over there has millions of neurons. And what you see is the average response across millions of neurons. And it's difficult to say what is happening at individual units. And so next, but in the neural networks, it's a bit more easier because you have access to response of individual units, and you could play around with those units, analyze them, and interpret, try to understand what's going on in these units over the course of word recognition process. So next we wanted to understand, okay, can we train these networks which are, trained to recognize words, and so, we can train the object recognition networks to recognize words, and then see how does they change. So for that, we used a very simple architecture, CONET-Z, and this architecture is loosely inspired to the brain, and different layers of the network correspond to different layers of the visual cortex. And so initially, this network was trained to recognize ImageNet images, and we call this an literate network. Now, in the second phase, once the network is fully trained to recognize objects, we introduce words, and now we train the network to simultaneously recognize both objects and words, images. And we have two variations of the literate condition. in one condition, we don't put any constraint. Like the output units receive the input from all the units of the previous layer. So we call this as unbiased network. In the third kind of condition, where we see biased network, we try to mimic like a word form area, which is like a localized region. So we said, okay, what happens if we like if this extra units, the word selective unit, the word recognition category units, receives only input from only a subset of the units in the previous layer. And so we had these three different networks. Now we train them to recognize. And so like because it's a simple network, the model performance on the objects is a bit low. But because the words are like, simple, like they're on a plain background, like they achieve like very high accuracies. And since we wanted to understand like how the word processing happens across different layers, we were not very concerned about accuracy and didn't try to optimize the network to have better accuracies. And okay, so once the network is trained, we try to investigate, okay, we did some of the experiments that you do with the fMRI or behavior. And so for the first question is like, okay, do these networks develop any word selective units or not? And for that, we like for each unit, we compared whether the activity for words, is it greater than the objects or not? And so you could put a different, so you could see like, if you just say, okay, if the response of words is greater than the objects, then we get some 20% of the units responding to that. But if like, and D prime here indicates like how many standard deviations is it above the word object response. So here we use an arbitrary threshold of 3, which means that there were 68 units out of 512 units, which are average pooled here, whose responses to words were 3 standard deviations more than the responses to objects. And 3 standard deviations usually like a 95% confidence interval. So that was the criteria that we chose. And next we wanted to like look at, okay, how does the network like, is the representations of the literate and illiterate network different or not? And so what we like used was, we look at the object response image for objects. We compared the representation space between all the 3 networks and across different layers. And we didn't see, although there's some changes in the later layers, but there's not much difference. But for the words, the representation in the illiterate network is quite different from the literate network in the later layers of the network. Although, while training the network, we didn't freeze or like only fine tune the last layers of the network. We like all the layers were kind of like open to, could change in theory to like adopt to have better word recognitions. But we see changes specifically in the last layers of the network. So we wanted to like first visualize like what are these changes. And also like because we didn't see any much difference between the representations of the biased or unbiased networks, we didn't analyze, we chose to continue only analyzing the unbiased networks for all the further analysis. So now, okay. So we wanted to understand, like, so we see like changes in these output last 3 layers. So we wanted to understand like what is changing. And so here we manipulated the physical properties of the word. So the word could be placed at any of the, so on a white screen, so because on a white background, the word could be placed on either of the 4 quadrants, as you could see. And if you look at this is, and we look at the population PCA across the layers of the illiterate network. So if you look at the illiterate network, and so you could see like, across in the IT layer, we see like, you could dissociate or like decouple the responses to, the responses of each quadrant are grouped together. And if you move a bit in the next layer, then we could see like there's a grouping based on the top versus bottom, like the yellow and dark blue are grouped together and the red and the cyan are grouped together. And that kind of is preserved in the output layer as well. And now if you like manipulate the size, then we see like these networks are like don't have invariant representations to size, and like the smaller size representations are grouped together compared to the larger size. And these networks, although weaker, they have some encoding of the word length. Uh, Now, doing the same analysis on the literate network, we see that in the we could see the changes, how it changes in the IT layer itself. Like here, all the grouping is quite. I mean, you could see like the grouping is based on left versus right. So the left, I mean, so the yellow and the red are grouped together compared to yellow, the blue colors. And this kind of like see like okay, so the words in the I think the it could kind of also indicate the object, the nature of the stimulus. Like in a real world scene, the top and the bottom parts are they change drastically, and so that's why the network learned to encode like top part of the image separately from the bottom part of the image. But in the case of words, the left and like the edge and letters are more important, so that's why the networks automatically learn to prioritize the representations of these things. And because the networks are trained to recognize words, they develop invariant response representation to changes in size. I haven't shown for font or other things, but they learn to have invariant changes across different physical properties. So next, we wanted to understand like, okay, what is the encoding scheme in these networks? So there are three possible things that we could think of. So if we take like two words of different length, there are different ways in which they could be encoded. Like because we read from left to right, we could see, okay, maybe they're aligned on the left letter, or maybe these networks, because these networks, they don't have any idea of notion of reading or eye movements. So maybe the word center model would be like preferred in these networks. Like where the center of the, because we have the words are showed at the center, then the rest, they would be aligned at the center. So what I'm trying to, or they could be edge aligned, where the response of words, I mean, as you could see here that like they would, I mean, the alignment would be like the lines, the edges are aligned and the middle letters are then later filled in. So if you try to fit, like if you, so what does this mean is that the response of, let's say the word read would be the linear combination of response of R at position 1, E at position 2, A at 3, and D at position 4. And in this case, the response of R would be the response of R at position 1, a response of E at position 2, and A at position 8, and position D and D at position 8 of the model. So here, I mean, we are trying to fit a linear combination model. And so the regression matrix that has 26 times 8 columns, where each letter has 8 possible positions it could take. And we would fill the regression matrix based on either of these three schemes. And then we try to fit the model with the lasso constraints, and then see how does the model predictions look like. And what we see is that on average, or in most of the cases, the edge aligned model fits are much better than the word center or the left aligned model fit. So we could, so this is the, what we have here is the unity slope line, and most of the points lie above this point, which means that like if the model fits at of the word center model, let's say is like 0.2, then they could, like the model fits of the edge line models could be like way much above 0.9. So this indicates that although these networks have no explicit notion of how should the words be encoded, they encode it based on the edge aligned encoding scheme. I didn't put any equations, but is this part clear, or I could try to explain it better if needed. Any questions? Okay. If not, I would go ahead. Okay. So we see that, okay, and the edge, the model, the nature of encoding of for these networks are the edge and aligned encoding scheme. And if you try to look at the receptive fields of the model with seven highest units with better model fits, then we could see some nice patterns. So there are some units which let's say letter S, and it doesn't change across different positions. So it will respond to letter S irrespective of, it would respond to word containing letter S irrespective of wherever the letter S occurs. And similarly, like this particular unit would be activated if a word contains letter U. But then there's some units which are not selective to any particular letter, but they're selective to particular position. So they would respond to letters like C, G, Q, or any similar curved shapes if they appear at the first position, but may not respond to when they appear at the other positions. And similarly, there are some units which prefer the last position and so on. And although this looks, so it's not very clear. Although there are some units with such clear selectivity to either letter shape or the position, but not all units have such properties. And there are some units where the model fits are not so great, and you could see and the selectivity is quite diverse. It's a mix of both letter and position, and it's difficult to interpret what that indicates. But in general, we know that they have edge-aligned encoding scheme. So the question is okay, we know that in these neural networks, they are based on the pooling operation, and the units in the previous the first layer has a very small receptive field. That is, they look at the convolution operation is applied on a very small part of the image. So they should be having an absolute coding scheme. And the later layers, we see that they have invariant response to position. So how does the network change from absolute position coding scheme to relative position coding scheme? And to dissociate that, we created a stimulus set where, if you look at this, we created 4-letter strings where one of the letter is the preferred letter of the unit, and the neighboring letters, the XXX, are the unpreferred letter. And what we do, so if you look at along the column, the word position shifts by one letter. So the dashed is the blank space. So along the column, the word shifts by one letter at a time. And along the row, the preferred location and the location of the preferred letter shifts by one position. So you could see that. So if it's OXXX, then XOXX. And if these units are encoding absolute coding scheme, then if you look at the response, then you would see more diagonal responses. Because if you see along the diagonal, the position of the preferred letter doesn't change. So if, let's say here in this case, let's say along the O is at position 4, then over here also O is at position 4, here also it's at 4, and same at here. So they would have more diagonal responses if the units prefer absolute position of the preferred letter and not the location within the string. But if they have a relative position coding scheme, then they don't care about where does the letter O occurs, at which location. They would respond as long as it's in the same position within the string. So it would respond along the column because the letter O always appears at the first position, although the absolute locations keep changing. And then there could be units which respond to the entire word, and they may not have any selectivity for letter X or O. And as we see in the later layers, it may respond to letter O wherever it appears. It doesn't care whether it's the first letter or the second letter. And so we would see response throughout. And so we had this kind of stimulus. And what I'm showing here is few example units of the neural network and the response profile. So what we see is so you would see, there are some units which have this diagonal structures, the response structures, and the receptive fields of, or the width of the diagonals keeps increasing along the later layers of the network. And this is quite evident because the networks are pulling the information from the previous layer. So they pull more and more information. So the receptive field size increases. And that's why the width of the diagonal or specificity of the position also increases across different layers of the network. But then we have some units which have these kinds of responses. So in the later layers, we saw, they have purely absolute position coding, so relative position coding. but in the previous layers, there are like selectivity to find some particular location at a particular position. So there are some very specific units. And the question is like, okay, do they also follow the similar profile of what we have pooling over here? Or is it something else? So it could so happen that these units like just prefer the blank space before them because they always appear at location 1, let's say. So they prefer the blank space before them, not the letter position coding units. So to differentiate between whether these units are blank space encoding units or relative position encoding units, we created another stimulus set where we introduce blank spaces between every letter. So we have the same stimulus as before, but only the difference is that there's a blank space between every letter. And if you look at the response, now if you compare from the first if you look at this matrix, then this unit prefers location 5 because like absolute position 2 and 2, 3, 4, 5. So if you see this is 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, 5, 7, 6, 8. So this unit prefers location 5, this one prefers location 3. And we see that even over here. So this one prefers location 5, which is over here. So 1, 2, 3, 4, 5. And like this unit prefers location 3. And so this kind of matches what we saw previously as well. Like these are the units which kind of prefers absolute position of the letter, preferred letter. Now what we see, if we see for the units which have blanks, these units, we see that in the layers V2 and V4, they're no longer preferred to the first relative position. They like position 3 and in this case. But only in the IT, we start seeing the purely absolute, so relative position coding. So I'll put this again for comparison. So you could see like this unit prefers location 3. And so in all of these cases, the preferred position is 3, but the receptive field sizes increases over time. And we could see that over here as well. But here we see that these units encode blank space because as if we introduce a blank space, then they again start responding to the preferred absolute position and not the relative position 1. And so what we think of this blank space could be like, so this could be some of the units which could be like a high-low frequency detectors, like in the early areas, such that so the blank space could be the low frequency and the letters could be the high frequency. So so initially, we were confused. Okay, why do these networks have blank space? Letter position coding units. Could it be? And ideally, initially we were anticipating that we would not expect to find such units because intuitively we would think, okay, maybe the attentional regions kind of play a role to understand where is the letter starting. And it's not like in the feed-forward networks we would identify that. But upon further analysis and like looking at the literature, we found that, okay, there could be some this high-low frequency detectors which could kind of give rise to blank space coding units and from which pools together to give rise to relative position coding units. And to summarize, what I showed you was like reading kind of, it's not like you learn to read like the words have special status and they're processed together. In fact, they're processed in parallel. And I have other studies as well to support this evidence. And we saw that the perceptual space of strings are encoded from in the lateral occipital areas and not in the early visual areas. And these regions encode relative position coding unit. And also like we see the semantic space in the language areas as expected. And word familiar is the place where the response times are for the lexical task is being encoded. And to summarize, we see that the nature of encoding of the strings is in general compositional, where the response of words could be predicted using single letter responses. And thank you for your time and stay tuned to understand like further. Any questions or?
Yeah, thank you very much, Dr. Agarwal, for insightful talk and participating.
I hope it was clear and not too heavy. For non-neuroscience audience.
Yeah, actually, I am a bit of from neuroscience and computer science, so for me it was okay. But let's hear from our audience. How was it for them? Okay, so
Hi, sir.
yeah, go ahead.
Yeah, this is actually a really good session, and the concept of word recognition and brain, it's pretty interesting. So I was just
Thank
thinking,
you.
yeah, I was just thinking how we could extrapolate this concept to brain-computer interface, like for example, thought to text conversion, etc. Or is it too far-fetched? What's
I
your
mean, yes. Um, so all of this insights is useful and they could be applied for BCI, but the issue is that if you want to do it non-invasively, like using EEG, then it gets very challenging because the signal to noise ratio decreases drastically. But if you say, okay, if you want to use patients, then like where they're undergoing brain surgery or people who are willing to go brain surgery to put these chips in their brain, then there are a lot of such evidence nowadays that, I mean, in the research papers which have come out, that you could do BCI on languages, like you could like think and write the message on the screen. So there have been recent publications on that, and it is possible.
Oh, okay. So
So if
EEG
you
it
want,
will
I
be a
could,
bit difficult, right?
yes. I mean,
Yeah,
if you
yes.
want, I could share some articles with you for your reference. But
Sure.
people have shown that like they would imagine handwriting, the like writing, they would imagine writing, and on the screen they would see the letters being printed, and so it's pretty accurate on some of the patients.
Oh wow, that's great.
Yeah.
Thank you.
Okay.
Could you share with me, please, too, like the articles you mentioned? How
Yes.
can I contact you later?
Sure. I mean, I'd share with Deepak, and he could share it with the audience if later.
Yeah, sure.
Okay. I mean, if you have any questions related to talk or in general neuroscience questions or any other thing that you want to ask, please feel free to do that. And if you didn't understand or if you want to have general gist of it, I could try to maybe explain it in like 2 line or yeah.
I have a question.
Sure.
It's not completely related to the
Mhm.
current topic that we're discussing, but it is based on neuroscience. Uh,
Yes.
I was just interested in concepts like like the fundamental basis of thoughts. What's the real nature of thoughts and consciousness, mind training, etc. But there aren't any real research papers out there which have like substantial information. I just wanted to know why that is the case, and if there's something which I'm not sure, you could throw some light on that.
No, I mean, there are quite a lot of, I mean, research work going on consciousness. Like my current supervisor also works on consciousness, and he has even written a book on that. So, I mean, it's kind of like more research oriented. So I think you could check that out. Uh, I could search and maybe put the link in the chat as well.
Sure.
Yeah. But I mean, it's a kind of research, and there are multiple hypotheses of how consciousness may arise. And I think Bengio is also nowadays interested in that, like to understand consciousness in the brain. Yoshua Bengio, yeah. You could. So, any questions?
So I have a question.
Yeah.
Can I ask? Yeah. So you get a formula, right? That the distance between the word is
Yes.
inversely proportional to reaction time, right? So is there any uh, component of memory, right? Like if some word we have seen earlier, right, and the word
Mhm.
we are looking for the first time, right? So obviously the memory will play some part. But in this equation,
Yes.
that particular part is covered,
Yeah.
right?
Yes. So if you see, like, I mean, when I say, okay, I'm doing a comparison between the similarity. So I'm assuming, okay, I have the template of the word. Let me pull out that slide. Um, just a second. And so if you look at uh, this slide, if you see here, I mean, I know the dissimilarity between, I mean, in behavior, I could estimate the dissimilarity between the actual word and the jumbled word. But when you see something, the incoming information is only for the PI and ICL. So to do this matching process, there should have been some stored template of what the pencil response would look like. Like here, I could model that using, because I could store the responses in my data. Like I know what the response of pencil would look like, what the response of the jumbled version would look like, and then do comparison between to find the dissimilarity. But when you see only one input, like P and ICL, then to have similar response time, it should do some computation inside the brain, some matching process. And I don't know how that happens, but that's where the memory component would come in, or some stored template of the word. Yeah.
Right. And then you also took neural network, right? So what was the input given there? Images?
Images again. So you show multiple images, image contains only one word, and the question is like, okay, can we predict the response to this image as a linear combination of individual letter responses?
Okay, and so is there any similarity between those images and the words?
And so the images were actually the words. So they were images of words only, like.
Also, images of the words.
Yeah. Here we didn't try to look at this kind of like comparison between the words and non-words. So we haven't. I didn't show it today, but we found similar evidence to that. Like depending on the similarity, the model foods would change, but yes, but they were like predicting the response of words using letters again.
Okay, and what if we give like text as an input to neural network, right? As in natural language processing we do. So
NLP kind of task, you mean?
Yes.
So that's a different domain. So then you get into the domain of grammar and all of those. So I don't know, so I'm looking at the step before that. Like once you assume, okay, you know what a word is, then you talk about like, okay, how do words combine to form sentence? So that's I'm not working on that. There are some people who are working on that to understand like the hierarchical nature of the sentence. Like you have subject, verb, object. So you need to assure, okay, this is the subject, and there could be longer sentences that where the first subject would like have some resemblance or action much later in the sentence. So like the combinations over there would be very different, and people again like studying. I could again send you references if you're interested.
Yeah,
like how do these words combine to form sentences?
Okay. Why I ask the question is like there are a lot of research in like how human process visual scenario and how neural network process visual scenario. And,
Yes.
But similarly, how human process text and how neural network process text, right? In NLP.
Yeah.
So there can be some.
Yeah, there are some work in that as well. Yeah, there's a lot of work going on in that.
Okay.
Yeah. So people again like try to like study resemblance between these two things, and again they also find out. Very briefly, I would say is like over there also people find that the networks which do good on the NLP task, like the GPT models, have better match to the brain responses to the language, like sentences and all of those. So they inside the scanner, they instead of showing one word, they show the entire sentence, and then they look at the response to that sentence and then try to predict the response using GPT model units, and or different model like transformer models, GPT BERT and all of those. And as the model complexity of the model performance improves, the predictability of the brain response also improves.
So, okay, so I have a question. Like that's a very abstract question, not related to this talk, but in general, that there are claims that okay, this AI is inspired from neuroscience, right? From brain and how the brain processes things. And now people are from these neural network. People are getting insights how the things might be going inside our brain, right? So
yes.
It's both ways. What do you think about it? Like, who is inspired from whom?
As you like answer, like it's both the ways. So the initial old models were like loosely the hierarchical nature, like having multiple layers of the network, that was or convolutional as the convolutional part. They say are like loosely inspired from the brain research in 1980s and all. But nowadays, like more like after that, the models that people have been building, like to predict the brain responses, we're not doing as good as the neural networks now. So people are now like trying to understand. Okay, they have got new toy. It's like, I mean, you have a new model like every year. Every decade, I think the model changes, and so earlier it used to be like SVM or like Gabor Feature Bank. I mean, there are a lot of different image features, but now we have deep networks, so we are trying to find we know that it works, but I mean, so the deep network community nowadays, I mean, I don't know how much inspiration they are taking from the brain, because most of the improvements that we get is more of a engineering the network to have better accuracies. But I would say that the next generation, so this is the kind of the feedforward networks are more of a, what you say, pattern matching, like they're doing pattern recognition kind of task. So they don't do a lot of reasoning or, I mean, more complex the way the human brain works. So the next generation of artificial intelligence networks that would come, which could do solve logical reasoning, abstract representations, those again would need some inspiration from the brain. So, I mean, we don't know how soon that would come, but I think that's an open challenge in AI as of now.
It like looks very interesting. All of these things, even
Yes.
hearing.
Yeah, it is. Yeah, I mean, it's exciting times. Yeah.
Yeah. Okay, so there is another question from Jasmine. Jasmine, could you please turn on your mic?
Sir, I just wanted to ask, like if we study like the people with dyslexia, would it give insights on word processing? Like, would it help?
Yes, yes. I mean, so that's also some of the work that I'm currently working on also. But again, and dyslexia is a broad term for a lot of, I mean, a lot of things that could change in the dyslexia. So it could be like at the visual level where they don't follow this rules of understanding, like, and sorry, so in the visual dyslexia, it could happen that the letter responses are not separable. Like, I mean, the response of words, they don't process the letters in parallel, and the influence of one letter interacts with the presence of other letters, and so that's why they have difficulty to dissociate what letters are present. But then there could be other related to, like, again, reading is conversion of symbol to sound, so they could have issues in the sound part as well, like from translating from symbol to sound. And so there could be different level issues which could give us to dyslexia, and there have been studied a lot of things over there as well. Yeah. I mean, if you're interested, I could have a separate, I could discuss it with you separately. But yeah, and I hope I answered your question.
Yeah, thank you, sir.
Thank you.
So, sir, if it is possible for you, you could drop your mail ID because people are asking me.
Okay.
Yeah.
Yeah. Could reach out on this. Yeah.
Okay, so
Please.
is there any preprint related to this work?
The neural network part or the which part?
This work related to compositionality of letter shape.
So the behavior and fMRI part is already published, and the first part of the, I mean, in the neural network part, the first part of that is also published. The later part where we try to understand how does the relative coding arise in the brain, like, sorry, in the networks, like from absolute to relative position coding. So that part is new and that is not yet out. But the remaining part are all out there. I could send you the references as well if you need.
Yeah, sure, because I got some requests from the audience.
Sure. I'll share the references.
Thank you.
Yeah. If anyone has any question, I mean, I have time, but the others, if they want, they could leave. But if anyone has any question regarding neuroscience or not related to this topic, they could feel free to ask.
So, okay. So anyone have any question related to like, okay, how to like, because I have seen the registration, so there are people in the audience who are in 12th class itself, right? Like, so from 12th class, first
Okay.
year, second year to the PhD, postdoc, etc. So we have
Okay.
wider audience. So anyone wants to know other related to this talk, or if you want to know like how to get into neural-inspired AI or whatever, you can ask. Feel free to ask your question. Yeah, Mary, you can unmute yourself.
Hello again. I wanted to ask, like, what skills do I need to learn, like, in order to understand what you were talking about during the presentation?
So I mean, the multiple things. I mean, so I mean, if you look at the neuroscience part, then I think you would need to understand like this first the terminologies, like because I mean, when I switched from engineering to neuroscience, like I had the difficulty to understand different terminologies of like. So that's one thing I think you would need, and it would be again like I mean to understand a lot of this modeling aspects, you need to definitely know linear algebra and like some of the basic mathematics related to that, like often and also like how the neural network is organized architecture and the net. I mean the network architecture. So if you have some idea related to that, then it would be very easy to follow whatever I said. Yeah.
Okay, I see.
Yeah. I mean I could. Yeah. I didn't go into a lot of details of each and every step of how I did the modeling part because that would have taken a lot of time. So I just showed some overview of what the results of the model was. But yeah, to understand the model, I would had need a lot more time.
What about computational analysis?
I mean that comes with the practice, I would say. I mean, like even the fMRI data processing or the building up these models. I think if you like take any of the available data sets, like if you just take my paper, let's say the data is available online. If you try to rewrite the code on your own, and I think if you do it once, you'll be confident enough to do it again. So I think it's more about practice. And if you know any programming language like MATLAB or Python, you should be able to do that easily. Yeah.
Yeah, so like people have those who are not from neuroscience joined because they have interest in this brain, right? Like, so
yes,
and then AI and then brain, they both are very interesting.
Yeah. Yes. Yeah, I mean, it's kind of right now. I think neuroscience needs more of this AI tools to understand brain. Like there are a lot of insights which comes by understanding this AI, this networks.
Yeah, and I'm just wondering that you have your bachelor in electronics, right? Then how you just got expertise in both the field, right? Like this AI and then neuroscience field both. How was it?
I mean,
Just your
it
journey.
didn't happen. Like it's been like 6. I mean, it's been 8 years since I left electrical engineering. So I think when I switched first, I switched to neuroscience. I took 1 or 2 years to like a lot of coursework to understand all the neuroscience terms and I mean all the what you say terminologies or how to read science papers. Because if you see like some of these experiments, the controls are quite important. Like to dissociate between absolute, let's say absolute and relative coding, the correct stimulus is important. Otherwise, you cannot tell okay what has been encoded at what place. And again, to dissociate if it's space coding or relative position coding. So to develop, I mean, it comes with practice and also like I mean, basically like it takes time to get that. So first I learned neuroscience, and while learning neuroscience, I got interested in. I was always interested in artificial intelligence. That's why I got into neuroscience. Like I wanted to reverse engineer the brain, and like so then I studied artificial intelligence in my own time. So whenever I got free time, so and eventually it's with practice it came to me, and I like neuromatch was also very useful.
Okay. So thank you very much. Basically, same is happening with me as well. So I can resonate with your story.
Yes.
So anyone else have any questions or should we wind up? We are running out of time. And I'm just thinking that like about this journey, right? from starting from your bachelor's and PhD, and then getting a best PhD award at ISC, and then now postdoc, and then now you will be soon a professor, right? So we are planning to have one more session with you, right? Because you will be the best to have. So we have so for other participants as well. So we have a big event at the end of the year around, right? So you just stay tuned. You will get to know about this, and Dr. Agarwal will love to invite you there as well.
Yeah, thank
For
you.
meta research event if you will have time. Yeah.
Sure. Yeah, sounds good.
So I would like to request the participant to turn on their cameras so that to have a group photo if possible for you. Thank you. If possible. Okay. So kindly turn on your camera so we can take a picture together. Okay. Okay. Anyone else? Anyone else is turning the camera because we are about to take the picture. Yeah. Okay. 1, 2. Okay. Thank you very much, everyone. Kindly fill in your attendance in the link given in the chat box. And if you have any more questions, then there is a mail. You can get the mail ID from the chat box, and you can also reach out to us as well if you want to get the resources which Dr. Agarwal was talking about. Okay.
Yeah, thank you all for attending. And
Yeah,
it was
and
nice interact.
so thank you very much, Dr. Agarwal, for answering all of the questions, and we are really thankful to you for cutting us your time from your busy schedule. And like
It's
I know that you will be participating in Euromatch as well. So so there are some preparation regarding this as well going on. So thank you very much for your for taking out your time. We, the member of IEEE SBC committee, would like to show gratitude by presenting a virtual token to you.
Thank you.
Thank you very much.
Yeah, thanks a lot.
Yeah, and so on behalf of entire counseling, I would like to extend my heartfelt gratitude to our speaker, Dr. Agarwal, and all of the volunteers, all of the SEC members, and most importantly, all of our viewers to make this event successful. With that, I just conclude this event. Thank you very much, everyone, for joining.
Thank you. Yeah, bye.